So, have you ever stopped and wondered what your toaster has in common with, say, the entire global internet? I mean, it sounds kind of crazy, right? But it turns out they're both connected by this set of brilliant, totally hidden rules. Today, we're going to pull back the curtain, uncover those rules, and really see how everything in our digital world is linked together. Okay, let's start with this. It seems like a weird question, I know. One makes your breakfast, the other keeps your house from feeling like a sauna. But, believe it or not, these two devices show us a fundamental split in how machines are designed to think, or maybe more accurately, how they're designed not to think. You see, they're both what engineers call control systems. Basically, they're built to manage or command something else. But the way they go about it, well, that reveals this really critical difference that separates a simple machine from a truly smart one. Your trusty bread toaster is the perfect example of what's called an open-loop system. You set the timer, you push down that lever, and it just goes. It runs for that exact amount of time, period. It has absolutely no idea if your bread is perfectly golden brown or a burnt, smoky crisp. Its action is completely separate from the result. It's just blindly following orders. And really, the huge difference between these two boils down to one single crucial word: feedback. An open-loop system, like that hand dryer on the left, is a total one-way street. It acts, but it never ever checks the results. But a closed-loop system, well, that's way smarter, because it's in this constant conversation with itself, always checking the output and adjusting what it's doing. Which, of course, brings us to the air conditioner. This is a classic closed-loop system. That little thermostat on the wall is its sensor, and it is constantly measuring the room temperature. That's the output. If the room gets too warm, that feedback tells the system, hey, kick on. And once it hits that perfect temperature you set, it sends another message. All right, you can turn off now. It's a self-correcting, totally automatic loop. Okay, so that self-correction thing is pretty smart, right? But the real magic of our modern world happens when all these millions of smart devices need to talk to each other. And for that to work, they need something more than just their own internal feedback loop. They need a shared language, a common ground. So, just like a thermostat gives rules to one single device, we needed a set of rules for all devices to talk to each other. And this is where we get into these things called network models. They're basically the secret language, the universal rule book that keeps the entire internet from descending into complete and utter chaos. To solve this massive problem, the experts came up with a brilliant solution. They developed models that break down the whole complicated mess of communication into smaller, much more manageable layers. You can think of each layer as a specialist with one very specific job to do, and when it's done, it just passes its work on down to the next specialist in line. Now, the first major blueprint for this was the 7-layer OSI model. The easiest way to think about it is like a digital assembly line for sending a message. At the very top, in layer 7, your app writes the message. As that message travels down through the layers, it gets formatted, encrypted, put in an envelope with an address, and broken into little pieces, or packets, for easy transport. Finally, at the very bottom, it's converted into a physical signal, pulses of light or electricity, and zapped out into the world. Now, while that OSI model is a fantastic way to understand the whole process, it's more of a reference guide. The model that actually powers pretty much the entire modern internet is a more streamlined, more practical version called TCP/IP. And what's really wild is where TCP/IP actually came from. It was developed by the US Department of Defense back in the 70s for a project you might have heard of called ARPANET. They needed a communication system that was so tough and reliable it could survive a major crisis. And get this, that resilient design became the direct ancestor of the internet we all use every single day. You know, the absolute genius of TCP/IP is just how practical it is. It takes those 7 theoretical layers from the OSI model and squishes them down into 4 super efficient layers. It basically combines all the user-facing stuff into one application layer and all the physical bits and pieces into another network access layer. It's this streamlined structure that made it possible to build and grow the internet so effectively. All right, so we've got the rules of the road. But what are the actual roads themselves made of? I mean, how does a little packet of your data physically get from your screen to a server that could be on the other side of the planet? At the most basic level, all our data travels in one of 2 ways. It's either guided, meaning it's following a fixed physical path like a copper wire or a fiber optic cable, or it's unguided, flying through the open air as an invisible electromagnetic wave. Man, our wired connections have evolved like crazy. We started with those simple twisted copper wires for old-school telephones. Then we upgraded to the thicker coaxial cables for cable TV. But now, the real backbone of the modern internet is fiber optic cable, which sends our data as literal pulses of light through impossibly thin strands of glass at mind-boggling speeds. And then you've got the wireless world. Different kinds of waves do different jobs. You've got radio waves, which are great for broadcasting over huge distances. Then there are microwaves, which are used for these very direct point-to-point links between things like cell towers and satellites. And of course, there's infrared, the stuff in your TV remote, which is for super short distances. And that's exactly why you can't change the channel from another room. It just can't go through walls. So, we've got these control systems, we've got these logical rules, and we've got these physical highways. Let's put all of these pieces together and just take a second to appreciate the incredible foundation they built for our whole connected world. So think about this. Every single time you browse a website, there's a closed-loop system in some faraway data center, making sure the servers don't overheat. At the same time, the TCP/IP model is taking your request and neatly organizing it into packets. And then that data travels all the way to you over this unbelievably complex web of guided fiber optic cables under the ocean and unguided wireless signals bouncing through the air. It's amazing. And what does all that physical infrastructure actually get us? Well, a single one of those fiber optic cables can handle data speeds of over 1 gigabit per second. To put that in perspective for you, that is fast enough to download an entire full-length, high-def movie in just a handful of seconds. It's just staggering. You know, at the end of the day, it all comes back to this one simple, powerful idea. Without a shared set of rules and protocols, all we'd have are billions of lonely, isolated devices. It's these rules, this shared language, that transformed all of those individual things into the global connections that we all depend on. And that really brings us to a final thought. We've built this absolutely incredible system based on these foundational principles. But as billions and billions more devices come online, I'm talking everything from our watches to our cars to our entire cities, what comes next? How will these physical and logical rules that connect our world have to evolve to handle all of that?